Today we talk about residuals and calculating our least squares regression line. So, in most cases, when we have data, a line will not go through every point in the scatter plot. It's just not going to happen. When we collect data, it's almost never going to have a perfect correlation of 1. A good regression line gets as close to all the points as possible, meaning that it's making the vertical distances of the points from the line as small as possible. And that's what we call the residual. So here are the vertical distances of each point from a regression line. The residual is going to be the difference between the data value, the observed y, and the predicted y. Subtract those two things, that's the residual. When we write this regression equation, when we have a regression line, we are trying to make those residuals as small as possible. So here we have this problem that we looked at in 3.1 with the pack weight. We had this data, body weight of different students and their backpack weight in pounds. So that's what this scatter plot is representing for us. Here's our regression line. We're going to look at how do we come up with these numbers today. So if you're ever asked to show the residuals on a scatter plot, you're drawing in these black vertical line segments that go from the point to the line. Negative residuals would be below the line. Positive residuals would be above the line. That shouldn't be too earth-shatteringly different. Going down, it's negative. Up, it's positive. Bigger than the predicted value is positive. Less than the predicted is going to be negative. Now, when we do regression, we're going to use least squares regression. And we could draw different regression lines, but the least squares regression line is going to get the residuals as small as possible. And the reason we use squared regression lines is because, remember, we have some positive, some negative regressions. If we square them, if we draw these squares and minimize the area of each of those squares, that would be the square of the residuals, we'll have all positive numbers. And we're trying to make that sum as small as possible. We want the amount of error to this line from our data to be as small as we can get. So how do we do that? Well, we can use technology, and we'll use technology in a minute, but we can also use the means and standard deviations and their correlation to calculate this regression equation also. Here's how we do it. If we have data for an explanatory variable and a response variable, we can calculate the means and standard deviations, and we can calculate the correlation. We did that in section 3.1. The least squares regression line will have a slope and y-intercept that follow these two formulas. So the slope is going to be the correlation times the standard deviation of y over the standard deviation of x. The y-intercept will be the mean of the y's minus the slope times the mean of the x's. So let's actually do this for our example. So here's our data. We had calculated, or we can calculate, what the mean and the standard deviation are for each variable. So the body weight is my explanatory variable. The backpack weight is my response variable. We can find x bar is equal to 136.125. And the standard deviation of those x values can be calculated to 0.296. Y bar can be calculated to be 28.625, and the standard deviation of the backpack weights is calculated to be 3.462. We can also calculate the correlation. Remember that formula was 1 over n minus 1 times the sum of the standard values, the standardized scores for each of these, the z-scores. X minus x bar over sx, y minus y bar over sy. And just in case you're wondering, yes, ladies and gentlemen, these values, these formulas, I should say, they're in your AP formula packet. Here's the formula for mean, formula for standard deviation. This one we don't know anything about yet. Here is the form for regression line. Don't know anything about this one. Here's how we calculate the y-intercept, just saw that. Here's how we calculate the slope, just saw that. And here's how we calculate our correlation. So just something to be conscious of, that these formulas are provided for us. So right now, once you pause the video, make sure you can calculate the correlation. What you should end up with is 0.795. So, how do we find the slope? The slope, we go back to our formula sheet, is r times the standard deviation of y over the standard deviation of x. So 0.795 times 3.462 divided by 30.296. Crunch those numbers, you've got the slope. How do we get the y-intercept? Call it A, call it B, 0, call it whatever you will. But the way we get that, if you go back to our formula sheet, is the y mean minus the slope times the x mean. So 28.625 minus whatever we got here times the x mean, 136.125. And there we'll have our slope and our y-intercept. We'll be able to write a least squares regression equation. Y hat equals whatever the A is plus whatever the B is times x. And let's jump to our graphing calculator and make sure that we can do this there also. So here I have the data values put into a listing spreadsheet. I'm going to go to Menu, Statistics, Stat Calculation, Linear Regression, number 4. My X list is body weight. My Y list, pack weight. I'm going to save the regression equation to F1, that's fine. Results, they're okay to put into D. I could put them into C if I wanted. There's nothing in column C. I'm going to push OK. There is my y-intercept. There is my slope. There's that correlation that we calculated by hand. And notice it tells us what the residuals are too. So there we have it. We've got this r squared thing that we'll talk about later, but there's the big ideas. We can also, remember, add in a data and statistics page to make a scatter plot. And we could show that linear regression right here. There's those numbers that we just calculated by hand. That's where we're stopping today, ladies and gentlemen. We can calculate our least squares regression equation both by hand and using technology. Congratulations, welcome to the big leagues. Have a good day.